Hey, we're going to talk about mass, energy, and temperature and how these things are all related. First of all, something we talked about at the beginning of the year. What is mass? Mass is anything that has matter, anything that you can interact with physically. Matter is made up of electrons and protons and neutrons. What is the difference between mass and weight? Well, if you go into space, you can become weightless. However, you didn't get any smaller. You didn't lose any of those electrons, protons, or neutrons. You have the same mass, but you do not have the same weight. Weight is mass times gravity. And you'll see as we go along that there will be a similar kind of idea when we're talking about energy. There is a law of conservation of mass. Mass cannot be created or destroyed. It can only be transformed. In a chemical reaction, the mass of the reactants equals the mass of the products. And, you know, we've seen enough chemical equations and reactions by this time that we know that, in fact, the different atoms, the bonds get broken, rearranged, but they're all still there. We balance equations. All the mass is still there. However, on a more conceptual level, it can be a little bit difficult to grasp because we think, for instance, you know, if we burn wood, well, what happened to the mass? Well, it got burnt up, combustion reaction. Some of it is turned into CO2 and water. We have the smoke, we have the ash. If we were able to contain all of those products, the mass would still be there. It's just clearly been transformed from the solid wood into other forms. There is also a law of conservation of energy. Energy cannot be created or destroyed. It as well can only be transformed. Now, what is energy? Well, the ability to do work. And in science, work is defined as using force to move objects a distance. We have an equation here, W equals F times D, the W for work, F for force, the D for the distance. The units for work or for energy are joules or calories. 1 joule equals a Newton meter. Newton is the unit of measure for force, meter, metric unit for distance. And 1 calorie equals 4.2 joules. Now, this calorie is not the same calorie that you would find on packaging for food. You look at the wrapper of a candy bar, you might see that it has 150 calories on it. But those are capital C calories, which are actually kilocalories, meaning 1,000 of these small c or lowercase c calories. And so, in fact, if we wanted to say how much energy you were eating, instead of saying maybe 150 capital C calories, it would be 630,000 joules of energy that you were eating in the form of chemical energy when you ate that candy bar. And obviously, much bigger numbers people don't really want to deal with. It's much easier to just say, you know, it had 100 calories, not 420,000 joules. Now, there are all sorts of forms of energy. We have solar, power and electrical, waves, combustion again, fire, mechanical energies of various sorts, and of course, chemical energy in the form of food. We eat food to give us our energy that we can use at a later time. In general, we tend to break energy into two main forms, kinetic energy and potential energy. Kinetic energy is also called the energy of motion. Its equation, 1/2 mv squared, where the m stands for the mass and the v is for velocity. So the faster that something moves, the more energy it has. The bigger something is, the more energy it takes to get it going to a certain speed. Think in terms of, say, small cars and big trucks. And then we have potential energy, the energy of position. And that's basically seen in two forms. On the right there, we have potential energy equals mgh. Sometimes that's called gravitational potential energy. The G is for gravity. And basically the idea there is when we lift something up, if we were to let go, of course, it would fall due to gravity. So lifting it up, holding it up, we are working against gravity. And so the potential there for it to fall the moment we let go of that restraining force is the form of that potential energy. M again for mass, the H in this case for the height. The higher we lift it up, the greater the potential energy. If gravity was greater, say on a different planet than on Earth, that could also be a factor in increasing the potential energy. The equation on the left is for spring-like objects. That could be a spring, a rubber band, a bungee cord, anything in which you can either compress or stretch the item out of equilibrium. The K in this case stands for what's called the spring constant, and that generally depends on the material and how tightly it's wound. And then the X is how far you move it out of its equilibrium potential. But again, think springs. If you were, for instance, to say sit on a bed, the springs in the mattress would compress, but the moment you got back up, they would pop back up. And it's that fact that they could pop up the moment you got off, that's the potential energy part. And generally what we find is that many items are essentially going back and forth between the kinetic energy and the potential energy. In other words, to lift that weight, it takes movement to pull it off the ground and put it into the air. So using kinetic energy, but then once it's in the air, it's now been transformed into potential. If you were to let go, it would then fall, and then that potential would be transformed back into kinetic energy in the process of falling. If it's moving, it has kinetic energy. There are some things that basically are both all the time. Some roller coasters going up and down. Again, anytime you're moving, you have kinetic. Anytime you're going up, you have potential. So moving upwards, you would have both. Pendulums as well go back and forth between transforming from kinetic to potential and back. When the pendulum is at its lowest, it's going its fastest, but it also has no potential energy at that point. When it is at its highest, it stops, no kinetic energy, but it has all the potential energy to start falling again. So, what is temperature? Temperature is a measure of the relative kinetic energy of the particles in an object. If you think back to some of our previous units, when we looked at gas laws and we would talk about pressure. Pressure comes from the collisions of the gas molecules with each other and the sides of the container. Increase the temperature, the gas molecules move more quickly, there are more collisions, and the pressure goes up. So there is a direct relationship between temperature and pressure. Even in our last unit, we were talking about equilibrium and how if you raise the temperature, you could make the reactions occur more quickly. So again, remember, kinetic energy is related to how fast things are moving. And so it is a measure of the kinetic energy in objects. Hotter objects have more energy than colder objects. And that's even part of our everyday speech. We talk about getting warmed up in order to be able to perform at a higher level. What is heat? Heat is energy. And in fact, when we were doing our last unit and we would look at our chemical equations, which might have a plus 36 kJ on one side, say the product side of the equation, and I'd say we can call that heat or energy. Heat is energy. It is the amount of energy in an object. And truthfully, the best way we can measure how much heat is in something is because it flows from areas of high temperature to areas of low temperature. And we can measure the changes in temperature and then from that be able to tell how much heat something has gained or it has lost. So what is the difference then between temperature and heat? Because honestly, sometimes we think about, how hot is something and we just give it a temperature. Well, think of it this way. How much energy would be needed to heat a pool versus how much energy would be needed to heat a cup of water to the same temperature? Well, there's a lot more water in the pool than in a cup of water. And so you would need a lot more energy to raise the temperature of the pool, say to 80 or 90 degrees Fahrenheit, than you would a cup of water. And in fact, we have an equation for heat. It is Q equals mc delta T. The Q stands for heat or energy, M for the mass. So there's that mass component again. C is called specific heat. And the little triangle, that's delta, that's a Greek letter. That stands for change in, and of course the T for temperature. And when we talk about the change in temperature, delta T, it's the final temperature subtract the initial temperature. And please note, if the final temperature is lower than the initial temperature, in other words, it got colder, then that delta T part will be negative, which means the Q will be negative. And again, when we were in our last unit, sometimes looking at the equilibrium problems, we would get a delta H, which would be a negative number for exothermic reactions, because in fact, the system itself had lost heat. That heat had gone into the environment, into the air, a negative number because it got colder. Likewise, if something absorbs energy, if it's more endothermic, it would in fact be a positive. It would gain heat. Now the C itself depends on the material. So for instance, for water, C is 1 calorie per gram degree Celsius. or another way of saying that is it takes 1 calorie of energy to heat 1 gram of water 1 degree, or 4.2 joules of energy to heat 1 gram of water 1 degree Celsius. Other materials, say metals, are much smaller C's, specific heats. They might be like 0.42 or 0.21, so they can be heated up much more quickly. They also cool off much more quickly than water does, which is one of the reasons that water can be used as a coolant, whether that's in your car or for a nuclear power plant, because it takes so much energy to actually raise the temperature of the water. So we've talked a little bit about exothermic and endothermic before, but let's broaden it up a little bit. Exothermic reactions release heat. Combustion reactions, for example, burning wood or coal. However, also realize that freezing of water or condensation are also exothermic reactions. Now that can seem a little contradictory because you're like, well, wait a minute, freezing, it's cold. But the whole idea here is it got rid of some of its heat. That's why it freezes. The colder it gets means it has removed or given away some of the heat that it had inside the water. That's an exothermic process. On the other hand, endothermic, you know, how do we melt ice? Well, you got to warm it up to get it to melt. So it absorbed some of that energy and therefore could be melted or even evaporated or boiled. You know, you heat it up in order to evaporate water. And so those are endothermic reactions. And so one of the things that you have to understand about looking at exothermic and endothermic is there's really 2 parts. There is the system that is gaining or losing heat, and then there is the surroundings, the environment. And so when we burn something, we feel the heat that is being released out into the environment. You know, we can be several feet away from the fire and still feel the heat, but if it's going outward, then that means that the material itself has to be losing that heat. So the system that is combusting is losing its heat, but the surrounding area is gaining it. Likewise, we might, you know, feel something, you know, a coal pack, for instance, it feels cold to us, but it's withdrawing or absorbing heat from the surroundings internally into the system, and you know what we feel is that withdrawal or that absence of the heat. And just to go back a moment, you know, if we think in terms of Q again, for exothermic ones, where it's losing heat, its temperature would fall, Q would be negative. For endothermic, where it is gaining heat, temperature is going to rise in the system itself, and so Q would be positive. Now, temperature is somewhat arbitrary. Kind of depends on what temperature scale we're using. Celsius was created basically to give a kind of metric sense to a temperature scale. We said freezing of water, instead of being 32 degrees Fahrenheit, would be 0 Celsius. And boiling, instead of being 212, would be 100 degrees Celsius. And you see the equations there to go back and forth between Celsius and Fahrenheit. The Q equation, of course, is written to be based in Celsius. So we'll always have to change it into Celsius if it's not already given to us that way. The Kelvin temperature scale is also called the absolute temperature scale because when we are at 0 Kelvin degrees, there is no energy, not even at the atomic level. The electrons cannot be moving around the nucleus at that point because that would still be kinetic energy. So we haven't actually been able to get anything all the way down to 0 Kelvin, but we can get things pretty close. And of course, you will use these equations on both of the sheets for homework. Now, if energy cannot be created or destroyed, how can energy be lost? You'll sometimes even hear the expression, you know, we lost some of the energy. Well, generally speaking, it's not destroyed, but when we say it's lost, it means it's lost to the environment or transformed into something that's not usable. You know, when cars crash, some of that energy in the crash gets transformed into sound, into actually heating up material in the process of the crash itself. You can't really say any of that was usable energy. A lot of times energy is lost due to friction of surfaces that are moving against each other. However, if we could stop the energy from being lost, if we could contain it all, and then we mixed two items that were at different temperatures, well, the hot item would have to get colder because it would lose some of its heat to the colder item. And of course, the colder item would warm up. Now, if we do this with water, 2 samples of water, we can throw out the C's, the specific heat, because it'd be the same for both samples of water. They're both water. And what we're left with is a way that we can basically solve for anything that would be unknown in this situation. For example, what we've got written on the screen here is the C's stand for cold and the H's stand for hot. And so if we mix hot water and cold water together, well, obviously the hot water is going to cool off and cold water is going to warm up. And after a while, we just have warm water. You can't really separate it anymore. But you can figure out what the final temperature of the warm water should be based on knowing how much cold water and how much hot water, those would be the masses, and what their beginning temperatures were. You can then do a sort of weighted average to find out what the final temperature would be. And it turns out that even though in the labeling here, the TFC, final temperature for the cold water, and the TFH, final temperature of the hot water, look different in the equation, they actually have to be the same temperature. And if you look for a moment on the board there, I in fact just went ahead and made them both T's, and so you could solve for the T's if you knew all the other information. You will in fact use this equation on problems 8, 9, and 10 of your worksheet, that the second one that was handed out to you. You put in the masses, you put in the initial temperatures, and you solve for the one final temperature. Or, say for problem 9, there you're given the final temperature and you solve for what maybe was the unknown temperature of, say, the hot water. Now, we could also do this same equation with, say, putting metal into water, but we would have to put the C's back into the equation because the metal and the water would have different specific heats. But we could, for instance, heat up a piece of metal, put it into water, and calculate how hot the water should get based on, again, how much metal there was and how much water there was. Now, all objects radiate energy. You're radiating energy right now. The table that you're writing on, the chairs you're sitting on, the floor, they're all radiating energy. But hotter objects have more energy than colder objects do. And generally, when we touch something and it feels cold to us, it's because there's that difference in terms of how much energy is radiating. Basically, radiated energy comes in the form of what we call electromagnetic waves. And you can see the electromagnetic spectrum there on the screen. We have radio waves and microwaves. These are the longest waves. Basically, the radio waves are anywhere from centimeters to tens of meters. And then on the other end, we have our X-rays and gamma rays. These are N for nanometers, and the A there is called angstrom. That's actually 10 to the minus 10. So that shows you just how small those waves are. On the other side, you have what are called frequencies. Frequencies basically are how fast the wave vibrates, goes back and forth. And they kind of go in opposite directions. So things that have the longest wavelengths have shorter frequencies. Things that have shorter wavelengths have higher frequencies, because it turns out that all electromagnetic waves have the same speed. That speed is the speed of light, 3 times 10 to the 8th meters per second, 300 million meters per second. And so if we were to take a wavelength and multiply it by its frequency, we would get about the same number. It turns out that energy is related to the frequency of a wave. So the higher the frequency, the more energy it has. And so again, you know, another way to think about it too is the more energy in something, the higher the frequencies in the waves that are being radiated outward. And so, you know, something like a human body would tend to radiate in the, say, infrared, think infrared glasses, part of the spectrum, whereas, you know, stars are going to be much hotter, and they're radiating at, you know, much higher frequencies, ultraviolet, visible light, ultraviolet X-rays, and even gamma rays, the highest energy type waves that we encounter. It's also true that wavelength is related to temperature. And we have a little equation down here for wavelength times the Kelvin temperature, and then 0.0029 is a constant. And what that allows us to do is, in fact, be able, by looking at, again, frequency and wavelength and then temperature, to tell how hot something is by the type of waves that are radiating from it. And so, for instance, we can use the fact that frequency and wavelength, energy and temperature are all connected to, for example, tell that one star is hotter than another star based on, for instance, what part of the spectrum we can see, whether that's more in the infrared, visible spectrum, ultraviolet, X-ray, whatever, because those would be higher frequencies, more energy. More energy means they're hotter, and we can relate that to its temperature. Even just for color, it turns out that the reds are not quite as hot as the blues. And so all these things are related: temperature, energy, wavelengths, and frequency.